Hi, welcome to ESI 521 Pattern Generation at the Nanoscale. I'm Professor Ukjun Nam at the Pennsylvania State University. So we will keep talking about Unit 3 Advanced Lithography, Nanoimprinting Lithography. So from this lecture, we're gonna talk about UV nanoimprinting. So this is the part 1 for the UV nanoimprinting lithography. So this is the outline for this lecture. So we're gonna talk about the UV nanoimprinting lithography system. And then this is step and flash nanoimprinting lithography system is one of the UV nanoimprinting system. So, but this is a very high potential to be used for commercial production. So we're gonna talk about more in details about these techniques, the UV step and flash nanoimprinting lithography. So this is the overview of the UV nanoimprinting lithography. So like the thermal nanoimprinting lithography, it is simple and then it offers high resolution. And then potentially it is very high, suitable for a high throughput process. And then like the thermal nanoimprinting lithography, it also can transfer 3D pattern if those kind of 3D patterns are formed on the master mold structure. And just as simply compared with thermal nanoimprinting lithography, this UV nanoimprinting lithography has much less possibility of the damages and then contamination on the master mold because it will use a much lower temperature. In most of the cases, it uses room temperature. And then it also uses very negligible pressure or no pressure for that imprinting process because the major driving force to cure that UV sensitive resist is an UV exposure. So that is why we can use very small very low temperature and then very small pressure for this UV nanoimprinting lithography. And then this is the biggest difference between thermal nanoimprinting lithography and the UV nanoimprinting lithography. In the previous lecture, we talked about how difficult to align two patterns on the master mold and then patterns on the substrate using thermal nanoimprinting lithography. But this UV nanoimprinting lithography, it does not have any issue for that alignment. So this is the big advantage, just simply compared with the thermal nanoimprint lithography. So you may remember this system. I showed you this system for the thermal nanoimprinting lithography. Actually, this tool can also be used for UV nanoimprinting lithography. So in this case of that, there is an UV lamps on the top. So we load the sample the same way we discussed in the previous lecture. The major difference between the thermal nanoimprinting lithography and UV nanoimprinting lithography using this same tool is after we spin coat that photosensitive resist on substrate, we put that master mold and then we will wrap this master mold and then substrate with a plastic bag. But this master mold should be transparent, so when we apply the UV light, those kind of UV light can pass through the master mold and then eventually cure this resist. And then we also need to apply some pressure in this kind of a system. So as to the pressure application, for this type of the system, its pressure range is kind of very similar to that thermal nano imprinting lithography. So let's talk about the step and flash nano imprinting lithography. So this is the one of the example of the tool using this kind of thermal nano imprinting lithography. So basically the system looks like this. So this is the stages, and then here is the imprinting head. So imprinting head has an kind of holders positioning the master mold. Actually, this is the much bigger picture of this head. So there is a place holding this master mold. In this cartoon, it just said template. And then here is the mirror, and then there is a source for the UV light, which is an eye line spectrum. So upon this master mold touch the resist on substrate, we just apply the light and then just cure the resist. And then the way of it is kind of working, as the name implies, it works like a stepper. So if we have a big wafer, in the previous system, we coat the resist at one time, and then like the thermal nano imprinting lithography, using the system like this, the size of the substrate is the same as the size of the master mold. So for this type of the nano imprinting lithography tool, after one exposure and after one press, we can just transfer all the samples, all the designs on the master mold to the substrate at one time. But this type of the step and flash lithography system, it does not coat the resist at one time. So like the stepper works at the optical lithography, it just spread the resist first, and then just locally finish the one pattern transfer, and then moved, and then repeat, and then moved and repeat. So using that way, you can just fill entire wafers, something like this. So this is the master mold. It's kind of very hard to see because this master mold is kind of very transparent, made out of quartz. So this light purple is just a case. So the actual quartz master mold is something like this, and then this is the specific master mold used for the step and flash lithography, and then the parent area is only positioned in the middle, something like that. So its structure looks like this, and then this area is kind of a little bit higher than this background big box. So it is looks like made of two box structures. So the bigger box is like this, and then we put actual design in the small box located in the center of the big box. So this is the typical process step for the step and flash lithography. So as I just briefly mentioned, it has some kind of a reservoir holding that kind of a resist. So before we do anything, we dispense that kind of resist, like on multiple different volume of resist drops. So once we just put these kind of drops of the resist, we slowly lowered that master mold that I showed you in the previous slide. But in this case of that, we don't have to apply any pressure, as this master mold is kind of getting closer to the this kind of resist drop. This is a substrate, and as it just going closer like this, this small drop of the resist using the capillary force, it just pulling the master mold, and at the same time as this kind of a small resist drops are pulling the master mold, it also just connected each other and then just forming one big drop. So once this master mold just coming down, and then once this kind of resist becomes just filling the all the spaces, then we apply UV light, then this liquid phase resist becomes a solid phase by the UV exposure, and after that we just separate this master mold, and then this is a separation, and then we moved to the next spot, and then dispense the resist, lowering the master mold, UV exposure, that cures the resist, and then separation. So this is the kind of a repeating step until whole wafer is filled by this kind of patterns. So again, it looks like a very similar. The stepper is working for the optical lithography. For this one, the bubble pattern formation is very important. So the bubble pattern formation is an all distribution of deciding the distribution of this kind of resist drop, and also should decide the volume of this kind of each of individual different kind of resist drop. So the goal for using this kind of multiple different volume of the resist drops to fill one unit area is when those kind of mold coming down, and then when these all small drops becomes one single drop, what we want to do is the imperfect world or optimize the bubble patterns, as all these kind of bubbles drops are connected each other. It just to perfectly fill one unit area. If the distribution of these drops are not optimized, and then if the volume of the drops are not optimized, instead of filling these all uniform, all unit areas, it can just make partially not filled one area, or it can overflow outside of this area. So what happens is, in this case of number one, this area where we don't have this resist will become a defect area, because there's no resist present, so we cannot transfer the patterns in this area. If this kind of a number two case is happening, what happens is, as we just discussed in the previous slide, after finishing one pattern, we move to next place and then fill another one, and third and fourth. So if we just so this is the optimized kind of based on the optimized bubble pattern. But if it overflows, all these kind of unit local imprinting designs just mixed up, and then those kind of overflow will cover the already patterned area, and then will make a defect on that overflowed area. So to prevent from that defect formation, the most important thing is that somehow when we lowered the master mold and then just merging all these kind of small resist drops, ideally you should fill this unit area uniformly. So to make that kind of a uniform distribution of the one drop of the resistor bubble, sometimes we put much smaller volume in that area which which does not have a sufficient kind of amount of the resist, or we decrease the volume size or things like that. So that is the one of the very important process for this step and flash lithography. But once we optimize this bubble pattern, we don't have to change all this kind of bubble pattern for pattern to pattern. So once we just optimize this bubble pattern, we can use the same pattern for the all nano imprinting process when we use the same size of when we use the same master mold. So this is the one-time optimization per master mold. So once we have the optimized bubble pattern, we can just keep using these patterns from that point. So this is the little bit more, little bit better version of the step and flash lithography tool, but the basic mechanism for transferring the patterns to the substrate is the same. So resolution is kind of pretty good. It can just demonstrate this 32 nanometer or lower. And then the alignment accuracy is on 10 nanometers, smaller than 10 nanometers. So it's kind of a pretty precise alignment. And then it can handle those kind of big wafers, 8-inch and 12-inch wafers. And then it also has a field size. The field size is the one small kind of a unit area, and then its throughput is on 4 wafers per hour. So one of the major reasons why it takes this kind of a long time of throughput is as to the even for the stepper used for optical lithography, we spin coat wafer already. So we don't have to drop those kind of resistor bubbles like this. But for this kind of step and flash lithography, we cannot use this pre-coat resist. So every time we need to do the nano imprinting, we should dispense this kind of liquid resistor drops to a local area. So this kind of a dispensing time takes most of the process. So that is why it takes much longer time for processing the wafers. So considering all those kind of stepper can handle, which can handle about 100 wafers per hour or more. So this 4 wafers per hour is kind of a little bit slow. But just considering this kind of resolution and alignment margin, this is kind of pretty close to the conventional stepper used for commercial chip production. So this is the one of the issue we want to discuss. This is the cost of operation. So this is a cost needed to operate each of this kind of a tool. So this is an immersion is the stepper optical lithography tool, and then this is an extreme UV tool. So compared to this kind of a two optical lithography tool, its cost of ownership is kind of much small for the nano imprinting tool. So like the multiple beam e-beam lithography tool, we can just put more nano imprinting tool, step and flash nano imprinting tool, since it is kind of a much lower cost of ownership. So using that way, using the multiple tools, we can increase those kind of throughput. So we can, adding more tools, we can increase the number of the wafers can be processed per hour. So this is the process flow. So this is the standard process flow. So on substrate, sometimes we want to put some planarization layer. Depends on how rough topography those kind of a substrate has based on the previous process result. So this is an optional layer. And as you may remember, for the master mold, we want to coat one nice mono layer of the anti-stiction layer. And we talked about the purpose of this anti-stiction layer coating in the previous lecture. But this anti-stiction layer is also needed for the UV nano imprinting lithography. So if we want to do the pattern, we first dispense this liquid type resist, and then lowering the mold, and then apply the UV, and then remove the separation of the master mold, and then we can just remaining this kind of a structure. So the pattern on the master mold and then the pattern on the substrate in this case is reverse. In other words, the cavity area in the master mold becomes some columnar structure on substrate. So if we want to transfer the cavity structures on this substrate, there are two options. One is we just make a new mold, which can give the opposite kind of structures like this. So these structures, the columnar structures, will automatically make the cavity structures on the substrate. Or we can replicate this master mold, then the replicated master mold will have an opposite structures. So based on that, using those kind of replicated master mold, we can have the same type of the narrow cavity structures on the substrate. This specific step and flash lithography can make reverse patterns just simply adding one more layer. So that's pretty interesting. So this is the way, using the same kind of a master mold, we can achieve this kind of a nano cavity as well. So the process to achieve this kind of same reverse tone, what we can do is from this point, it is the same. Using the master mold, this is the master mold. So first thing we need to do is dispense the resist fluid, and then lowering the master mold, applying the UV light, and then upon we separate it, we have this opposite pattern. So once we have this blue resist pattern, we spin coat another layer, this yellow resist layer, and then we do the dry etching. So roughly we etch at this interface, and then upon this interface of the etching, we just change the plasma, and then we just further etching. And then in this case of that, we can just selectively remove these blue areas, and then eventually those kind of nano trench areas becomes making a nano trench area. If then what's the secret of the selective etching between this yellow and blue? So the secret for that kind of a selective etching is this yellow resist containing a silicon nanoparticle. So what happened is this blue resist we used for the UV nano imprinting. These are all made out of the organic polymer. And then this yellow is an polymer plus silicon nanoparticle. So when we etch these two materials at the oxygen plasma, this silicon nanoparticle mixed resist, which is yellow right now, has much slower etch rate than this blue area. So that is why those kind of a different kind of etch rate make a selective etching on this blue area only, and then it can just making the trench structures, this kind of nano cavity structures, only on this blue area. So that is the secret for transferring two different tones of patterns using one single master mold. So for this one, since we don't use too high pressure, it is almost no pressure, and then it is operated at the room temperature. So it has much less chances for damaging on this master mold. So using this way, we can just, this is a third way, we can just achieve this kind of same type of the patterns using one single mold. And one of the big issue for the advanced lithography is we discussed about this in the previous lectures as well. That is when we need to use this kind of fine patterns for the following processes like dry etching or liptop process. So when we need to use this kind of a fine pattern as an for example dry etching process as a following process, we always need to have a very high aspect ratio of nano pattern. But as we discussed, as this kind of a thickness of the resist is kind of getting thicker, it's kind of very hard to achieve very high resolution of pattern definition. So what we can do, actually, for that reason why people just use liptop process, and then using this kind of a liptop process, people just put the hard mask, which is the metals or dielectrics. So when we use this hard mask, even though the thickness of this hard mask is kind of thinner than that of the this kind of polymer resist, but as to the etch selectivities, its etch selectivity is much higher than that of the polymer mask. So it can provide a much higher aspect ratio of the dry etching. What you can do using this UV nano imprinting lithography is we can use some planarization layer. So that is a little bit thicker, kind of another polymer layer. So after we just transfer these kind of patterns, after the nano imprinting, this UV nano imprinting also remaining very thin polymer layer between the patterns, and then we also need an autoplasma cleaning. In another word, we call this autoplasma cleaning as a descoming process. So after this cleaning process, we can achieve this kind of nanostructures we want to achieve. But the thickness of this imaging layer will not be as thick as we want. So if we want to achieve much higher resolution of patterns, using this green imaging layer as a mask, we can just dry etch and then just to transfer the green patterns to the blue patterns. So using this way, we can just make much higher aspect ratio of the nano patterns. So since we have a little bit more thickness in the resist side, so we can etch a little bit further to the substrate. So this is the one of the way we can achieve this kind of high aspect ratio of nano patterns. So this is based on this cartoon showing that all ideas. This is an actual experimental result, and then what we are seeing right now is an field emission SEM images. So this is an after we complete the nano imprinting, and as you can see, there is some layers left between the actual parent transferred area, and then during the oxygen plasma cleaning, we remove this bold area, and we just this is all green patterns showing in here, and then we can just transfer these patterns, and then we can finally achieve this kind of high aspect ratio of nano pattern. And then using that patterns, this FESEM pictures shows even after finish the substrate etching. So this is the UV curable resist, and then this is the transfer layer. So this is the bottom layer, and then using this way, we can just do the further etching. So this is a side view, and this is the top view, and yeah, this is just before the substrate etching. So the substrate etching was not happening yet. Sorry about that. So it is just right before the substrate etching. So as you can see from the top, it does not have a line edge roughness issue. And this is a kind of a very important issue. Just considering those kind of a contact optical lithography or those kind of a projection optical lithography, we are always talking about light diffraction. As I just briefly mentioned in the early of this lecture, to cure this resist, we also use the same kind of wavelengths of the UV light, like an eye line. Then why we do not discuss about this light diffraction for the UV nano imprinting lithography? One of the factors is those kind of optical lithography when we transfer the patterns on the photo mask, actually the glass is something like that, and then the light passes through this kind of a transparent area, and then we talked about the distance of these openings and then the wavelengths, and depends on that kind of dimensions, the diffraction is kind of getting more affected on that finite resulting area or things like that. So the light just passing through the mask which has the images, and then those kind of light which already kind of interact with this kind of pattern having a photo mask, it just transferred to the resist, and then there is some kind of another kind of a reflection or sensitivities of the resist. Those kind of things are another kind of an issue, making those kind of patterns bigger than its designs or things like that. But for the UV nano imprinting, it also has its own design on the master mode. But major difference between this UV nano imprinting lithography and then optical lithography is this design formed on the master mode just physically transfer its shape to the resist. So the role of the UV light exposure is just simply curing this UV sensitive polymer becomes much harder. So there should be a diffraction issues, or there is a light diffraction as we just blank expose all this kind of a totally transparent master mold. But those kind of diffractions does not actually affect on that pattern dimension changes or line edge roughnesses, because all those kind of patterns are physically transferred by the master mold. In other words, those kind of patterns on that resist just to simply mimic the pattern on that master mold. So even though we are using the same wavelengths of the UV light for the UV nano imprinting lithography, we don't have this kind of a light diffraction issue in the UV nano imprinting lithography. Let's talk a little bit about the alignment. In the earlier slide, I showed the alignment margin of this technology is kind of smaller than 10 nanometer. So what happened is this is the nano imprinting. So one good thing is this master mold is transparent. So that is why we can see through the master mold, and then we can just align these alignment markers on the substrate as we are doing for the optical microscope, optical lithography. So we can just simply use the same techniques used for the optical lithography, and even for this kind of step and flash lithography, this resist material is liquid form, because when we do the alignment, it is before we apply the UV light, so that is why the resist is still liquid form. So even when we move around this master mold, this kind of a liquid form of the resist can work as a lubricant. So that is even help for this kind of alignment. So that's the biggest advantage compared to the thermal nano imprinting lithography. So just considering the way we can just fill all that kind of a big wafers using the step and flash, and then using this kind of precise alignment capability, and then those kind of another kind of high resolution capability, this step and flash lithography has very high potential as an next generation lithography technology. So today we talked about the systems used for the UV nano imprinting lithography. So we talked about those kind of air cushion type, and then we also talked about the step and flash lithography. So as we discussed, this UV nano imprinting lithography offers high resolution, accurate alignment, and then relatively high throughput. And then like the thermal nano imprinting, this UV nano imprinting also can transfer three-dimensional images with one single nano imprinting process. So since that UV nano imprinting lithography use a much smaller pressure and then much lower temperature, even can be done in the room temperature, so it has a much less problems for the contamination and then damage issue on the master mold. But for this master mold should be made on the transparent material like quartz or glass, which is a much harder material than silicon. So as to the making the master mold fabrication, it is much more challenging, and then we will discuss about the way of making the master mold in the next lecture. Okay, then see you next time.